I've kept it a little bit generic topic just because I will include most of the part from my PhD work. And now that I've shifted to the postdoctoral research, so that area is also related to the gaseous dielectrics, basically the alternatives. So I'll be covering a bit about that, the present work that I'm doing. I will not be able to share much of the work because nothing is published yet from the current work. But yeah, I would like to share a general idea about the gaseous dielectrics and the alternatives that are present, like in today's scenario. Here's a brief introduction about me. So, as Ashok has already told, I have done my B.Tech from National Institute of Technology, Silchar. Thereafter, I joined Sterlite Technologies Ltd as a design engineer in the power cables division. I worked there for a few years. After that, I pursued my master's plus PhD integrated degree from Indian Institute of Technology, Guwahati. And further to that, I have joined at the University of Manchester as a postdoctoral research associate, where I'm currently carrying out my research. So I would like to start with the alternative dielectrics, so which is basically the insulation that we are talking about when we are talking about transformers. So transformers, which forms a crucial element for the reliability of any power system network, as we all know, and also the efficiency depends on the transformer at various stages. So small difference in efficiency can lead to huge power loss. So in the transformer, there are many components. So there's the core, the winding, the tank, and the insulation. My research is basically focused on the insulation, which is the mineral oil, along with the craft papers and press boards. So I will be mostly focusing on the mineral oil, which is the liquid part of the insulation. So the insulation usage is limited by its breakdown strength, which is also the maximum electric field beyond which they become highly conductive. So in the diagram, we can see how the evolution of the transformer oils or has been in the recent years. Like it started at the at the Gans factory in 1884, and how it moved on from paraffinic to naphthenic MOs, then the PCBs, then silicon oil, synthetic esters were introduced, then there were the natural ester based products, then how nanoparticles are also researched with the vegetable oils. Then there are the aging studies that are going on, and the research further continues with the natural ester oils, the other synthetic esters, and also the mixed oils, the blended oils, and the nanofluids. So we know that in a transformer, there is the transformer oil, and there are the paper and pressboard, which is the cellulosic insulation. So in due course of time, sludge formation takes place. So with that, the thermal and the insulation properties degrade. Also, if there are any air bubbles or contaminants are present, discharges may tend to develop. And in due course of time, the breakdown strength of the oil decreases because of the formation of other particulate matter. So we see how the degradation happens in the insulation system. So T1, T2, T3, and T4 you can consider as the temperature. So T4 is a higher temperature, and then we have here T1, T2 in small letters. So these are the times. So as the temperature is more, it is very likely that the physical property of the insulation degrades at a faster rate. So we can see this from the graph. So this is just a idea about how the degradation occurs when the thermal stress is increased at a higher temperature. So now why alternatives are required to the mineral oil? So the mineral oils have been used in the transformer for a very long time. However, they have very lower fire resistance capability, and with the growing power demands, the need for alternative dielectrics is rising. The non-biodegradable nature of mineral oil also leads to hazards in the environment. So studies are going on for the development of a new dielectric liquid, which is suitable insulating oil to be used in a transformer. Researchers are going on for considering the nanoparticles to be dispersed in the mineral oil to enhance the properties of the oil, as the heat transfer capability of nanofluids are superior than the existing mineral oil, which has been found from the research. And many researchers are still going on to analyze the property of the natural ester oil because of its many advantages, as they are biodegradable, they have higher water holding capacity, and also they have the higher flash point. So keeping in mind all these things, so the alternative to the conventional mineral oil is of utmost necessary. So here we can see the advantages of the alternative oils. So natural ester oils are biodegradable, so there is less harm to the environment if a spillage, accidental spillage occurs. Also, the flash point of natural ester oil or the vegetable oil is much higher than the conventional mineral oil, so the chances of catching fire during some untoward incident is very less. So natural ester oils have higher breakdown strength as well in spite of the dissolved moisture levels because of its ability to hold moisture. We can see from the graph that how in like 30 days, the biodegradability has been around 95% for the natural ester oil, which is quite low for the mineral oil. Also, from the second graph, we can see that the natural ester oil has the water saturation limits at around 60 degrees. We can see that as compared to mineral oil, it is around 10, around maybe 15 to 18 times more water saturation limit of the natural ester oil. So they have enhanced heat capacity, so cooling is not a problem. The breakdown voltage with the nanofluids is higher than that of the mineral oil, so which reduces the probability of breakdown. Also, improve thermophysical and electrical properties. So alternatives oil. So we thought of an idea like alternative oils to the mineral oil is necessary. Either it be the non-edible natural ester oil or the nanofluids. But to prove that it is equal to the mineral oil, we need to do some aging studies of the natural ester oil as well as the condition assessment of the oil considering all the required tests to be done on the oil. Also, we need if you're going for the nanofluids, we need to study the effect of the nanoparticles when they're added to the oil. So first of all, we'll see how non-edible natural ester oil and its nanofluids can be developed in your laboratory. So we did the research on it and how from scratch we can develop a natural ester oil, whether it be edible or non-edible. We focused on the non-edible part. So we developed a non-edible natural ester oil and which performed quite good when compared to the mineral oil. So here is the production of the processed natural ester oil. So we chose the Pongamia oil, which is the crude oil, which is got from the seeds of the Pongamia plant. So, but this oil in its crude form cannot be used for usage in the transformer because of its high fatty acid content. So this oil, which is like from the seeds it's collected, the crude oil, it needs to be converted to the Pongamia oil methyl ester, or you can say it as the fatty acid methyl ester form, so that it has like comparable qualities or the to the mineral oil. So first we go about the seed collection, then there's the drying process, then removal of the bark, then extraction of the crude oil. So from here we need to do the filtration, the chemical processing, vacuum drying, then we obtain the natural ester oil, which is in the form of fatty acid methyl ester. So here it's a process, so it's a long process but can be carried out in the laboratory where we have done it, and uh, you can try with different types of seeds or different types of oil, and just to check if somebody is doing research on oils, then this is a very interesting process and they can just go about to see how they match with the mineral oil or all the commercially available vegetable oils that are present in the market today. So we took the crude oil here, then we first measure the free fatty acid value. If it is greater than 1%, uh, if it is yes, then we go for the acid pre-treatment where we combine it with methanol and a catalyst. So for the acid pre-treatment, we use the H2SO4 as catalyst. It's added to the oil. So the separation of water and the formation of monoester. Then again, the FFA value or the free fatty acid value is determined. If it is like not less than 1, then we again carry out the process once again until the value is less than 1. So if it is less than 1, then we go for the base transesterification process, where we again use methanol with the potassium hydroxide, or you can also use sodium hydroxide, and it's added to the oil. Then the separation of the glycerol takes place by using a centrifuge at 6,000 rpm for 10 to 15 minutes. Then Pongamia oil is formed in the upper layer and water is washed for the removal of impurities. And this is how we obtain the final form of the natural ester oil, which can be used for the further tests. So here what happens, the vegetable oil or the natural ester oil, it's formed by the fatty acid chain, which is it's a triglyceride which has 3 fatty acid chains combined with a glycerol molecule. So under the presence of methanol and a catalyst, they form the fatty acid methyl ester and then the glycerol molecule. So this is what we are concerned about. So this is a fatty acid methyl ester, which is in the purified form, and all the further tests can be carried out. So here are some of the basic properties of mineral oil, pongamia oil. This is the pongamia pinnata oil, which is the crude form. Then we converted it to pongamia. So we can see how some of the properties has changed when we have converted it to the fatty acid methyl ester form. And this is the FR3, which is the commercially available vegetable oil from soybean seeds. It's developed by Cargill. Then this is the Jatropha oil, which is another form of natural ester oil, which we have procured from some local vendors to compare the properties with the mineral oil and all other natural ester oils. So, so we have got the two oils now, the mineral oil and the natural ester oil. So now we need to also develop, like we were focused on also developing the nanofluids by considering both the two types of oil. So for this process, we use the hexagonal boron nitride nanoparticle. So hexagonal boron nitride is a particle which is in a 3D form, and the size is around 1 micrometer, which is quite large when we are considering thinking about nanoparticle or the nano sizes of the particles. So we need to go for the exfoliation process to convert the 3D particle into 2D nanosheets. So we can see here how the 3D particle is converted to the 2D nanosheets, and this is confirmed by the transmission electron microscope images. So like a 1 micrometer particle, it's like converted to around maybe 100 nanometer or 50 nanometer particle. So for the exfoliation process, we take the 1 micrometer sized hexagonal boron nitride particle and it's dispersed in isopropyl alcohol. Then we go about with the process of ultrasonication at room temperature. Then it's centrifuged at 1500 RPM for 30 minutes. Then we do the vacuum filtration and vacuum drying to obtain the 2D EHBA nanosheets. So for the nanofluid preparation, we take the exfoliated hexagonal boron nitride and disperse in the mineral oil or the vegetable oil. Then we do the ultrasonication, then we shake it in a shaking incubator, then vacuum drying, and finally we obtain the nanofluid. So now we do the comparison of both the mineral oil and the pongamia oil methyl ester along with the nanofluid. So as we can see, by adding the nanoparticles, the AC breakdown voltage has increased quite a bit. For pongamia oil methyl ester, there has been a reasonable change in the AC breakdown strength. As you can see from here, the percentage increase of the AC breakdown strength of all the oils when compared to the mineral oil. And here's the uncertainty of measurements, which is quite okay because it's in the range of 1 to 2%. So now, what is the physics behind the increase of the breakdown strength when we are including the nanoparticles? So here is the charging dynamic study that was performed in many earlier works, and also we have tried to implement because we are using an insulating nanoparticle. So here is the electric field in the mineral oil. So you can consider any type of nanoparticle, whether it be conducting, finitely conducting, or insulating nanoparticle. So the electric field on the surface of the nanoparticle is given by this equation. We'll not go much into detail of the equation, but here we can see how it occurs. So when electric field is applied, so there are the negative and the positive charges because the nanoparticle is polarized. So with due course of time, the positive charges are neutralized to negative charges as electrons get deposited on the surface of the nanoparticles, and after the electrons get deposited, it becomes fully negative on the surface of the nanoparticle. So this process is known as the electron scavenging, by which the nanoparticles are able to capture the electrons on its surface, and this slows down the process of breakdown, and thus the breakdown strength increases. So here also we can see the two processes using a conducting nanoparticle. The values are slightly different because of the relaxation time constant. And here we can see the finitely conducting or the insulating nanoparticle. So we've taken an insulating nanoparticle, which is the hexagonal boron nitride. So the values are here as such. So here we can see the charging rate of the nanoparticle when we are using the insulating one. And by using any kind of software, maybe MATLAB or Mathematica, so I have used Mathematica. So here we get the charge deposition on the nanoparticle by these two equations. So one is with mineral oil, other is with Pongamia oil methyl ester. And in the graph below, we can see the deposited electrons on the nanoparticles when they're present in mineral oil or they're present in Pongamia oil methyl ester. From the table here, we can see how the charge per nanoparticle is given. So we can see that 423 number of electrons are captured per nanoparticle as compared to 354 number of electrons is captured when the nanoparticle is present in mineral oil. So this shows that as the nanoparticle, as the number of electrons are higher when the same nanoparticle is present in Pongamia oil methyl ester. So this shows that the breakdown strength of the Pongamia oil methyl ester based nanofluid is higher than the mineral oil based nanofluid. Also, we have done some experiments with the dielectric constant. So dielectric constant, the measured at the calculated values can be calculated by the Maxwell-Garnett equation. So this is a very simple equation where you just need to put the percentage amount of your nanoparticle concentration. We have a 0.01 percentage. Like too much of concentration or too much like concentration of the nanoparticles is also not very advisable, because after a certain point agglomeration tends to occur. So all the properties that could be there, it just begins to go like downwards. So also, when we need to consider the polarization of the nanoparticles, then this is a further formula like the Clausius-Mossotti equation, which can be used to calculate the relative permittivity of the nanofluids. Now, dielectric dissipation factor, or the 10 delta, it's also known as the loss factor. It's very much important property of any insulating liquid because it gives a measure of the dielectric loss. So when the temperature increases, the power dissipation is more. So the lower the value of the dielectric dissipation factor, the better is the integrity of the oil. Now, higher dielectric dissipation factor value, it indicates that the presence of contaminants in the oil. So it's seen from the figure, the dielectric dissipation factor decreases with the addition of the nanoparticles, which is quite desirable. So this may be because of the nanoparticles which captures the electrons, so the conduction current decreases and hence the losses are lower when the nanoparticles are added to the transformer oil. Now, thermal conductivity is also another property which is very much important when we are talking about the cooling of the transformer using the insulating oil, because that oil, it serves as an insulation as well as a cooling medium. So with the addition of the nanoparticles, we can see that the thermal conductivity has increased. We can see the percentage increase of the thermal conductivity when we are considering the mineral oil with the mineral oil based nanofluids, the Pongamia oil methyl ester, and also the Pongamia oil based methyl ester based nanofluid. So we can see how the thermal conductivity has increased. So this may be due to because of the nanoscale dimension of the 2D nanosheets of the nanoparticle. So it forms because of the surface area of the nanoparticle is increased. So it helps in the transfer of heat and thus the thermal conductivity increases. Now, interfacial tension, flash point, and pour point, these are also some of the properties of the insulating oils that are done for its condition assessment, as you can say. So we see that it's desirable that the interfacial tension should be higher or in the range of 40 to 50 for a good insulating oil. So in this case, the vegetable oils are not comparable to the mineral oil. However, with the addition of the nanoparticles, the interfacial tension tends to increase, so that it can be compared with the mineral oil. Also, for the flash point, as we all know, the flash point of vegetable oils are quite higher than that of the mineral oil. This may be due to the structure of the vegetable oils. Also, with the addition of the nanoparticles, the flash point increases. So this may be, indicate that because of the addition of the nanoparticles, the vapor generation is lower. Also, when we see the pour point of vegetable oil is also poorer than, is poorer than the mineral oil. However, with the addition of nanoparticles, the pore point tend to increase a little bit. So when the nanoparticles are added to the oil, like whether it be mineral oil or the vegetable oil, so it tends to disperse the wax crystals and that might have formed because of the lowering of temperature. But with the addition of nanoparticles, it slows down the process and hence the pore point is increased. So from this study, so it's seen that the mechanism behind the better properties is apparently the molecular structure of the vegetable oil. The esterification of the vegetable oil helps in lowering the viscosity and the pour point values, which makes it suitable as a replacement for the transformer oil. Dispersion of nanoparticles in the oil aids in enhanced AC breakdown voltage because of the electron capture on the surface of the nanofiller, and also the thermal conductivity increases. The charging dynamics study also shows how the nanoparticles helps in capturing the electrons. The variation of permittivity is also studied, and a comparison of calculated and measured values can be performed. The higher surface area of the nanoparticle leads to improve in the thermal conductivity. The pour point is comparable to that of mineral oil, but still marginally high, which can be improved by addition, like introducing additives. We have not used that, but it can be done. Flash point is of the methyl ester is higher than that of the mineral oil, which is highly important parameter when considering like no fire risk in the event of a major fault in the electrical system. So there has been use of vegetable oil commercially. As we can see, Cargill has FR3, which has been implemented in India as well. So Tata Power, I think they have installed a natural ester based transformer in Mumbai. So it uses natural esters. So yeah, nanofluids, it has a little bit of disadvantage with the fact that they tend to settle down over due course of time. So surfactants or other additives can be added to keep them afloat in the mineral oil to maintain their property throughout the course of time. So I think more research needs to be done in that area. However, natural esters are gaining quite prominence because of their different properties, and they are like comparable or are better in terms, are better when compared to the mineral oil. So we'll start see look into like the dissolved gas analysis of the new natural ester oil. So this is like one of the condition assessment methods where we see how the oil performs under thermal stress. So in my case, I have done only thermal stress study. So electrical stress can also be applied to see how the evolution of gases or the dissolved gases takes place in the oil when they're subjected to longer duration. So dissolved gas analysis, it's a very important tool in condition monitoring of the transformer in case of incipient faults, be it thermal or electrical. In my case, I have studied just the thermal faults, so I will be discussing only that. So the major gases which evolve in the transformer are hydrogen and the hydrocarbons like methane, ethane, ethylene, acetylene, and carbon oxides like the carbon dioxide, carbon monoxides, propane, and propylene. So there are various methods to study the dissolved gas analysis that has been going on since a long time. So IEC gas ratio method is there, Rogers ratio, Dornenberg's ratio, Duval's triangle. There is also Duval's pentagon method, which is developed recently and has been in use. So I have done the Duval's triangle method. So we'll be going on seeing how these all the methods perform on the selected oils for this study. So these are the different gases, and these are the primary and the secondary indicator of all the gases that we can detect in the oils when we perform the dissolved gas analysis. So for the methodology, so head sprays extraction method is used for the gas extraction, whereby the oils are put in sampling vials and the head space is purged with argon gas. Only the oils are put into the vials, and the argon is kept over the oils. Then they are agitated for a period of time, and it dissolve, and the gas that is dissolved in the oil escapes into the blanket of gas. And we can get a GC or the gas chromatograph, and we can study from the concentration of the gases that have evolved in the oil to do the further analysis. So for this study, I considered the FR3 and the Jatropha oil. So FR3 is the commercially available oil, and Jatropha is the one that's the non-edible natural ester oil, which we procure from a local vendor. So here we can see, so this is the aging setup, like how we aged the oil, and these are the vials that are used for the DGA. We can see how the color changes. So this is just for one oil, the FR3. So it's like light green in color. So with time, like 1,000 hours, 2,000 hours, so we can see how, like visually, we can see how the color changes. The 2,000 hours, the it's like becoming from light green to dark brown. So a single temperature technique has been employed where the oil and equivalent amount of solid insulation were subjected to thermal stress at a single temperature. So in this test, a seal tube was used for aging the oil samples, and we heated the vessel to around 150 degrees Celsius, and the oil samples were taken out at 500,000, 1,500, and 2,000 hours to analyze the various characteristics. So for the 150-degree aging temperature, so there is this formula we can by which we can calculate the loss of life. So this is 40.6. It's a factor which is given in the standard, so it can be used. And so for 2,000 hours, so we get a 45% loss of life. So for if you want to carry out for a higher duration, that can also be done. So there are different factors which are given in the IEEE standard, which can be used to ascertain the loss of life. So after doing the aging experiments, we needed to see how the structure or the chemical structure of the oil have changed or not. So so visually it was fine, like it changed from green to like dark brown, but like how much more, like chemically inside the oil, how much has it changed? So we used like two methods. One was the Fourier transform infrared spectroscopy, and another one was the nuclear magnetic resonance, which we'll discuss in the next slide. So here we used the infrared source, which was passed through a beam splitter, and there are two mirrors, like the scanning mirror and the fixed mirror, and then the beam one is reflected and transmitted, and it goes to a sample and it detects, and there is a fingerprint of the molecular structure which is formed. And here we can see like the percentage transmittance of the oil. So in the figure we can see like the chemical structure has not changed much, like for the FR3 0 hours, 1,000 and 2,000 hours. So the chemical structure remains intact, so it is like kind of a good sign, because there might be other impurities but the chemical structure has not changed. For the Jetrophy as well, we can see that the chemical structure has not changed much. So two peaks are observed for the CH stretching. So these are very much chemical terms that they use when you're using the FTIR spectroscopy, stretching and bending. So the CH stretching is observed for both the oils, and we can see like they both are vegetable oil. So the structure is kind of similar, like all these peaks that are observed are nearly around the same wave number. So the CH stretching is the presence of alkanes. Then around 1740, there is a C double bond O stretching. This is because of the esters present. So this is like a fatty acid methyl ester, and some amount of CH2 bending is observed around 1464, 1460 in both the cases. So, and these bendings and stretching are kind of similar when we are using a fresh oil and when we have aged up to 2,000 hours. So I have not done further testing like for 3,000 or 5,000, then there might be some changes in the structure. So if we'll do, then that might be like visible, but I cannot like certainly tell it now. But up to 2,000 hours, the chemical structure was still intact. We also did a nuclear magnetic resonance analysis where the sample is agitated by using RF waves, and then it is detected, a fingerprint of the sample is detected, and we can see how the fresh FR3 and the aged FR3, though here also it's kind of quite similar, like there has not been much change in the fresh and the aged sample. So we see multiplets are observed for CH3 and CH2. So these particular numbers, they correspond to a few functional groups like the CH3, CH2, which are, you can get it in any like references. So these are very much prominent. So two multiplets are observed for CH2 and CH protons of the glycerol in the range of 4.12 and 5 points. So we can see like these two uh, multiplets which are observed, and at 2.3 the presence of methyl ester. So this is one of the most important point where we see the presence of methyl ester, as the peak signifies the carbonyl methylenes. So this point is very much important, and so if this is not present, then we can be sure that there is something wrong with the sample, or like something has changed in its functional groups. And peak at 7.28. This is just the chloroform solvent that we have used, like this one. So there are the standard gas ratios. So for the dissolved gas analysis, so up till now it was fine. Like the structure of the gases have not changed, like while doing the FTIR or the NMR. But we need to find out, like if there are any incipient faults, like so how the dissolved gas analysis helps. So the standard gas ratios are this R1, R2, R3, R4, which are the ratios of the various gases like methane is to hydrogen and all this acetylene, ethane, ethylene, etc. So we can from these five ratios, we can formulate the IC and the Rogers ratio and the Dornenberg's ratio, which are few of the methods to analyze the dissolved gases. So here we can see this is a dual triangle. So this is another method which we use for doing the dissolved gas analysis. So as you can see, IC gas ratio methods, it uses R1, R2, and R5. Rogers ratio uses R1, R2, R5. Dornenberg's ratio uses R1, R2, R3, and R4. But the dual triangle uses, it's a different method where it uses a triangle, and the three sides of the triangle are denoted by the methane, ethylene, and acetylene, and they are used to detect the fault types. So you can see that there are boundaries present here. So all these zonal boundaries, they refer to one kind of fault. Here we can see, like at the top, it is PD, so P, partial discharge with low energy density. Then there is D1, this is discharge with low energy. D2, discharge with high energy. Then there is like mixed electrical or thermal faults. And T1, T2, T3 are all thermal faults relating to different temperatures. And this is the formula how the concentration of each of the gases are got, and they are plotted in the Duval's triangle. Now, Duval's triangle, when we talk about, it's not just one triangle. So for the mineral oil, there is a standard Duval triangle, which we can see on the left-hand side of the presentation. So this is the mineral oil. This is the triangle for the mineral oil. So here we can see the percentage of the gases which are given, the different zonal boundaries. So these boundaries are decided after carrying out many number of tests from the DGA and then plotting all the tests related to different kinds of faults in the Duval triangle, and then the boundaries are decided. So for the silicon oil, Midel, now this is the FR3 and Biochem. So we can see how the boundaries have changed, the red lines and the blue and the green lines. So the black lines are the ones which match with the mineral oil. However, for the other lines, we can see that it has changed for all the different types of oils. So this is how like the gas evolution patterns changed when we are considering different types of oil. So this may be because of the chemical structure, the molecular structure of the oil. So the middle is, I think, rapeseed oil, FR3 soybean oil. So biotemp is also different type of oil. So all these things changed when we are using different types of oil. So accordingly, we need to consider that triangle which is relevant to us, and to have a fair comparison. So from the test that I have carried out, so these are all the gas concentrations that were obtained for 500 hours, 1000 hours, 1500 and 2000 hours of aging. So after getting all these concentrations for the dissolved gas analysis study, like the from the gas chromatograph, so these concentrations were got and these were plotted. So we can see like the formation of ethane is higher in FR3, so this may indicate something. And in case of Jatropha, the carbon dioxide is higher, so this will also indicate something. So this we need to find out after looking at the ratios and the Duval triangle. So for the IC ratio methods, as we know that R2, R1, and R5 are used by the IC ratio method, so this is how the values are depicted, and there are certain codes which are given. So we need to take out the ratios, then go to the code and go to this chart, like how then we realize what the fault or what the incipient fault it can be after going from the concentration. So if this code matches like 001 or something like R2, R1, R5, so 001, it indicates like thermal faults for temperatures less than 150 degrees. So accordingly, we can do go and do the analysis. Also for the Rogers ratio method, the same three ratios are used, but in a different proportion. So here also we can see where the R1, R2, and R5 lies, and accordingly we can detect the type of incipient fall. Now this is dual triangle. So for the dual triangle method, we have used dual triangle 3, which is specifically denoted for FR3 oil. For Jatropha, no such triangle is available till now. Maybe after many tests or dissolved gas analysis are done, there will be a certain triangle which is like dedicatedly for the Jatropha. But for fair comparison with the FR3, since we are using both the two types of oil, we have used the dual triangle 3 only for the Jatropha oil as well. So here we can see, like in the dual triangle 3, all these concentrations, like as we can see from the earlier figure, like how the concentration is determined, the percentage concentration is determined when we are using the dual triangle. So here we can see all the faults, like all the oil at different hours lie in the same region. So it's T3 region, which indicates between 300 and 700 degree. Although the experiment was carried out at 150 degrees Celsius, but maybe because of the higher time duration, this might show that it uh, lies in a fault region where temperatures are greater than 700 degrees. So to see how it performs at the low temperature fault, which is like less than 150 degree, we used a dual triangle 6. This is also related to FR3, and it is related to low temperature faults. So here we can see that all the FR3 samples lie in the stray gassing region. This may be because of the evolution of ethane. And for the Jatropha, all the region lies in the overheating region. So So this is how the analysis can be done. So since we were doing the analysis at 150 degrees Celsius, so dual triangle 6 seems to be more appropriate when we are doing the analysis for the FR3 and the Jatropha. So this is the gas ratios for all the aged oils. So this is the IC gas ratio methods. So it detected somewhere thermal falls in some cases of Jatropha, and in some cases no falls for FR3, and in some cases it's PD. So all these ratio methods are not very accurate because sometimes they detect the falls and sometimes it's not proper. So till now, I think the dual triangle has been giving quite acceptable results when we consider the dissolved gas analysis. So it is one of the most important method when we are doing a dissolved gas analysis, and also the dual pentagon method, which is being used recently. So that can also be used when we are talking about the dissolved gas analysis. Okay. And another additional part when we're doing the dissolved gas analysis can be the total dissolved combustible gases. So here we consider the concentration of all the gases which are combustible. So CO2 is not combustible, so it's not considered here. So the addition of all the gases is considered, and we have plotted it in a graph. So the blue dots, we can see like the total combustible gases that are produced after 2000 hours seems to be higher in FR3 than in case of Jatropha. So this may be like a comparable results when Jatropha is compared with FR3, as it fares better when we are considering the total dissolved combustible gases present in the oil after a long duration of time. The oil consistency remains quite unaltered after 2000 hours of aging, which is a good sign when as confirmed from the FTI and MR results. So FR3 generates quite a significant number of ethane when thermal stress is applied. Also, the generation of hydrogen in case of FR3 is high as compared to Jatropha, indicating FR3 is more prone to stray gassing at 153 degrees Celsius. Jatropha shows higher concentration of carbon monoxide and carbon dioxide, but the ratio, so this ratio is also important when we are talking about dissolved gases. So these ratios are within acceptable limits, which confirms that cellulose degradation is not that much in Jatropha. The gas ratio methods are used to predict the fault types, but only the IC method predicts the thermal faults for Jatropha correctly. So as I have told that all these ratio methods are not very accurate, but however, with the Duval's triangle method, stray gassing is obtained by far and overheating in case of Jatropha. So it's observed that the total dissolved combustible gas in a filter increases sharply with aging time, and thus this makes Jatropha fare better in terms of total dissolved combustible gases. So, like more studies needs to be done when we are considering a natural ester oil to be implemented. So, like this is one of the condition assessment methods which can show like different simulated conditions can be used. Like here only thermal stress has been studied, but electrical stress can also be studied and combined with the thermal stress to get like more deeper insight into the types of oil before they are being implemented in the field. So yeah, so this was like some of the work that I did during my PhD, and these are being published. So, but now I would also like to give a little overview of the work, or a general overview, I would like to say, about the SF6 alternatives that I'm researching on presently at the University of Manchester. So yeah, so SF6, as we all know, like who are associated with the power system, they will know that it has excellent properties of insulation and arc interruption, and that's why it has been chosen for so many decades to be used in high voltage equipment. But people now are tending towards more environment friendly future because of its high global warming potential, because it's around 24,300 when compared to CO2. So to significantly reduce the carbon footprint, so the utilities and the manufacturers are implementing the SF6 alternatives. Many alternatives are looked into, which are mixed with oxygen, carbon dioxide, nitrogen, which are the natural origin gases, so that they can perform similar to the SF6. And these mixtures allow to build like state-of-art high voltage equipment on the same principles of the SF6 technology. And because of the high dielectric performance of the few of the selected mixtures, the equipment maintains like low material, minimizes the greenhouse gas emissions. So here we can see the greenhouse gas emissions which have been recorded over a lot many years, as we can see from the second picture, like from 1850 to 2020, the rise has been huge, simulated and natural. So this needs to decrease. So for the rise of these greenhouse gas emission, SF6 has been told as one of the main components because of its leakage, dielectric strength, arc quenching capability, thermally stable, non-toxic, and non-inflammable. However, a main drawback is the high global warming potential. So, as I've already told, it's 24,300 as compared to CO2. So there has been effort to reduce the leakage. The SF6 leakage are tend to happen since we are doing many gas handling during production, manufacturing, and like it uh, like the sealing systems that we are using in all the high voltage equipments are like they are there to keep the SF6 leakage under control, but it's not possible to eliminate the problem over like a long period of time, as they tend to lose their property. So there has to be some alternatives to the SF6 to be used in a high voltage equipment. So here we see the SF6 emissions tend to increase when there is like the electricity consumption increases. So this is data from some 22 countries that are using uh, like high voltage equipment. So we can see that the more electricity consumption is there, higher is the SF6 emissions. So unless and until there is any action taken to replace the SF6, or because electricity demand, it's very difficult to reduce the electricity demand. But if we get some alternative to the SF6, then the SF6 emissions are likely to be reduced. So for the potential alternatives to SF6, we need good like insulation, dielectric strength, high heat dissipation, low boiling point, low toxicity, so good arc quenching capability, non-flammability, like It should be stable, it should be readily available, and it should be easy to handle during the maintenance works. And above all, it should be comparable and better than SF6. So some of the alternatives that are being used is the C4F7N and C5F10O, otherwise clean air or synthetic air. So these are like fluorinated compounds which has like comparable properties when mixed with a buffer gas. And when compared to SF6, they show similar dielectric strength. But some of the points like the boiling point is lower as compared to SF6. So we need to combine it with a buffer gas like CO2 or N2 to come to a comparable position of the SF6. However, as we can see, the global warming potential is low, and when it combines with like a buffer gas, this further lowers down to maybe 400, 500 GWP, which is quite good. So researchers have been looking into like alternatives with C4 and C5 mixtures with CO2 or N2 or O2 and CO2, as the dielectric strength is also comparable, and then the GWP is also lower. So mostly the focus is on the C4FN mixtures for the high voltage equipment, because of when it's combined with CO2, like in 20-80 percentage, it gives a comparable result with the SF6. Also, the boiling point is lowered when it is combined with CO2 and N2. So CO2 is mainly the main carrier gas used for the insulation interruption, and it provides the highest arc quenching capabilities. N2 is not really used for the interruption, but the mixtures have low permeation rate when compared to the CO2, and so it's also a good alternative. O2 is also used in combination with CO2 to like eliminate the appearance of the free carbon solid byproducts which are produced when CO2 is used with the C4FN mixtures. So here we see like how with time, like C4FN and C5FK mixtures are being used. So from 2018, like the green ones are the C4FN mixtures. So the like number of bays or circuit breakers, so the number has quite increased. So this is a good solution, we can say, to this as regards to the SF6 alternatives. So first, like how do we select the alternative? So first, like there are many gases, you can say, like electronegative gases or something. So the low dielectric strength gases are eliminated, then the ones with high global warming potential are eliminated, then the toxicity of the gases, if known, the high toxicity gases are eliminated, finally the high boiling point. So we need to come to an optimum solution which can be used as SF6 alternative. And here we can see that the C4FN mixture at 6 bar, it's like quite similar with the SF6 at 5 bar. So like all the alternatives are not suitable to be used or retrofit in SF6 equipment. However, there can be a solution to this, provided we increase the pressure to a certain extent, keeping in mind the boiling point of that mixture. So a good potential alternative to the SF6 can be obtained. So, but however, in the recent, I think last year, there has been some regulations which have come into picture, that the European Parliament and everyone, they wants to put a ban on the PFAS. PFAS are the fluorinated gases that are available in the market. So it's all like back to clean air or synthetic air maybe, which needs to be used in further. But I think discussions are still going on, and I'm not quite sure about that, like what will be the scenario like presently. But I think up until, like for high voltage equipment greater than 145 kV, I think up until 2031, like these gases can be used, but still there needs to be a solution like regarding the ban. So yeah, so this is the talk about like this is all that I had to present today. Thank you very much for your attention.
Thank you, Dr. Niharika.
Yeah. Should I stop sharing the screen? Or okay.
Yes, please, you can.
Yeah.
I request all the people in the audience to write their questions and fill the feedback form. Write the questions in the chat box, please. Thank you for this informative talk. I think it was very beneficial for the all the researchers who are working in this area of research, or uh, all the people who are in general working in the dielectrics.
Yeah, also,
Uh,
yeah, you can get back to me if there are more questions or if there are any questions related to postdoc or something. So I would be happy to help. I think, email ID is with the organizers, and also I can maybe write it down here.
yes, please mention in the chat box.
Yeah. So,
While we hear from the audience about the questions, let me ask you a question which is not related to the presentation.
okay.
Where do you see this area of dielectrics in the next 5 to 10 years? What are the potential topics you see which will get more popularity, I guess?
For the dielectrics, I would say, like, if I talk about the gaseous dielectrics at this moment, I think because of all this ban and things happening, people are like focusing more towards the clean air. But still, if some solution comes out or if a new gas is developed, I see. So, like, alternatives will be there in the 5 to 10 years. And if a new solution or a new, because these are all like some kind of man-made gases, so if some solution comes up which has a low global warming potential or has better strength than the SF6, then yes, like there is chance of, and alternatives will be there, and it has to be there, I believe. So yeah, for the like 5 to 10 years, this is going to, I think, yeah, this is going to be there, the dielectrics, and more so the alternative dielectrics.
Yeah. Uh, a lot of research is going on in HVDC. So I think, what do you think? That area is also getting popularity.
Yeah, HVDC also you can use in HVDC as well, because like for high transmission you need. So if you can talk about gases, like they, but you need to consider like the pressure and the boiling point. It depends very much on the mixtures that you're considering, like the insulation part. So it depends on what mixtures you're considering, and for uh, doing the HVDC like researches. So this also is going to be there, and as I say, like different dielectrics are there, so you can use that and do your research on the HVDC part as well. And it's going to be, I think, interesting work, as I can see.
Okay. So, as being a researcher in the field of dielectrics,
Yeah.
what are the challenges and opportunities you face? Can you give some overview?
Uh, Okay, so as I can see, sometimes like we are doing research in the field, like, well, the availability. Sometimes I believe one of the most important aspects when we are doing research in the academics is that the industry interface is important, and that I feel is like you get to employ, because you're doing a research on a certain topic, like you take a liquid or a solid or gas, whatever dielectric it be. But when you need to like implement your solution, so it's very important that there is an industry to support you in such an area so that you can implement your research in the field. Because in the laboratory it's fine, you are in a controlled environment and everything, but when you are doing a research, because unless and until it's like applicable to the real world, it's of no use, right? So I believe like the first challenge is that it's very important that an industry collaboration is there so that you can employ your research in the field, and the industry is like the main, you can say, a support in that case. So that is one of the challenge, because only doing like research in the lab is fine to a certain extent, but yeah, so that is one of the challenge. And also the availability of resources is also important, because like you need lots of like big equipments for high voltage people. I think most of us know, like you need lots of equipments for doing, because it's not only like simulation. Yeah, obviously you can do the simulation and everything, but I have been mainly like an experimental researcher. So for me, like the availability of equipments is very much important. So that is also a challenge, maybe. So if everything is available, it's fine. Otherwise, yeah, you need to look for it, get projects and stuff like that. So that's it, I think.
Yes, I think most of us in the audience can relate and understand that we need industrial collaborations
Yes,
and
yes.
experimental research. So
Yeah,
there is a
yeah,
question in the chat box.
yeah.
Is there any potential of C4F gas for the reduction of very fast front transient amplitudes generated in the high voltage equipment at UHV class? As dielectric strength of C4F gas is almost too relative to SF6 gas.
So it depends, like at what pressure and temperature you want to use. Like C4 gas as a whole has a dielectric strength like two times that of SF6 gas, but because of its like low boiling point, I would say, sorry, high boiling point because it's around one minus 4 degrees Celsius. So because of that, it's not used alone. So it's like combined with a buffer gas to match the dielectric strength of the SF6 as well as to lower the boiling point. So it depends, like you want to use at what temperature, what pressure you want to use the gas. So I think because I have not like studied about the transients, but yeah, it can definitely be used, but you need to take the other factors into consideration as well, like the temperature, pressure, and everything.
I think that answers the question of Mr. Urukundu. If you have any questions, please reach out to Dr. Niharika.
Yeah, definitely. Yeah.
I would like to request the audience to turn on their camera if possible so that we can take a screenshot of everyone. तुम turn on, तुम ले लो screenshot. Okay, thank you very much. I would like to
Thank
present
you
a
so much.
small token of appreciation, and I would like to thank everyone in the audience for being with us. We organize monthly webinar. Uh, we have been organizing for about an year, and we will continue next year also. The field of this dielectric is very small in India and all around the world, so very few people join us, but still uh, we are able to communicate the knowledge through these small webinars. So please join us whenever you feel comfortable or whenever you see the topic is related to your area. Yeah, thank you, Dr. Masias.
Thank you. Thank you so much.
Please wait. My friend is trying to share the token of appreciation.
Okay.
So, I would like to ask one more question. For
Yeah.
researchers in this field of dielectrics, like we are the young professionals,
Yeah.
what advice do you have for us to start our career?
Like career in the academics, you're saying, or like in general, like industry
In
as well?
general, any tips for the career advancement?
Career advancement, see, it depends on what you want, like your priority. So if you want to go to academics as well as industry, I think there is a lot of scope in the high voltage domain. That is what I feel after coming here as well, because in the UK, in the Europe, like there's a lot of research going on. We also do a lot of research in India as well. So like from India, I did my PhD and I know like all the research that is going on there. So if you like think about joining the industry, it's also quite good. There's lots of things happening in all the sectors. So I think first of all you need to focus on your research. So if your research is good, you like got to take out a few publications in a good journals. That's I think one of the first things that you need to do, either because then like both the things are open for you, like both the academics and the industry, like you can go both ways. So for academics, obviously you need to do like good research, good papers. good projects. You need to get involved in good projects. And then after doing a PhD, like if you are joining academics, then obviously either you join directly as a faculty for, or you can go for a postdoc position. So postdoc position, I believe, like coming here, it has given me lots of exposure in the area of dielectrics. I got to meet many new people. I am learning different things because in PhD I was doing like liquids. Now I'm doing shifted into gaseous. So like your mind opens to many other things. So that's also one of the advantage. So if you're going into academics, I think that's like a good trend. So this is with my limited experience that I have. So like you take out good amount of papers, then do a postdoc, then either join the academics, or you can also go for the industry. Industry also has like lots of scope because they have the support, they have the money. So yeah, you can do lots of research. R&D is strong in the industry as well. So that is also another option. Yeah.
Yes. Okay. Thank you very much. I think there is some
Thank you.
issue with the presentation of the token of appreciation. We'll mail
Oh,
you the
no
same.
problem. No problem. Thank you.
Thank you very much. It was a very nice presentation. We'll
Yeah.
get in touch if in future you are.
Yeah, sure, sure.
We'll
No
call you
problem.
for
Yeah.
another webinar or a physical presentation in IIT Kanpur.
Oh, ah, sure. No, no problem. Yeah.
Thank you very much.
Thank you. Yeah.
Thank
Thank you
you.
everyone for joining. Yeah.
Thank you.